A very good morning and welcome back to my channel, which is Teacher Cool. पिछली वीडियो में we were talking about the particles and antiparticles, how the universe was made out of nothing, and hence we said there is a anti-universe existing somewhere which is exact opposite of our own universe, and hence we were basically discussing the concepts of particles and antiparticles. So without any further wasting time, let's start with our today's concept, which is particles and antiparticles. We say that for every particle in this world, there exists an antiparticle. But what are antiparticles? What are their properties? How do they interact with matter or the antimatter and among themselves, right? So the first thing is when particle and antiparticles meet. I said the universe was made out of nothing, and hence when this universe was created, there was some anti-universe was also created, which should vanish when these two universe and anti-universe collide with each other, and again there should be nothing. So similarly, we say when particle and antiparticle meet, they destroy each other and the radiation is released. Why radiation? Because when this collision occurs, the entire mass of these particles and antiparticles, which is conserved quantity, should be converted to some kind of energy, and this energy will be released in the form of a radiation, right? So this phenomena is used in PET scans. Now what is PET scans? So basically in medical science we have, just like CT scans or X-rays, we have a PET scan which is positron emitting आपका जो प्रोसेस रहेगा. So इसके अंदर the key product is your positron. Now what is a positron? And now we know what is an electron. So the antiparticle of electron, which is E positive, is known as my positron. This will be the symbol. So we say when we make use of a lot of high energy positrons and we inject these positrons into a body for the required scans. So what happens is these positrons, they collide with electrons, which are the antiparticles, and they just vanish and radiation is produced. Those radiations are then detected. They are very short-lived. So what happens? Like I have shown here, there is a particle, there is an antiparticle, they collide and they just radiate radiations. So what will happen? I'll say positrons are injected into our bloodstreams or in our body and they collide with the electrons and they radiate out gamma photons, which are then detected by our detectors, and this way we get our PET scans, right? Now, positron emission takes place. When does this positron emission takes place? We said that we are injecting these positrons into our body or into our bloodstreams. But how are these positrons emitted? The answer is the positron emission takes place when a proton changes to neutron. We know that electrons are in the outermost shell of the atom. Then we have a nucleus where we find protons and neutrons. Now, when we are talking about a large nuclei where we have a large number of protons and a large number of neutrons, so in a proton-rich nucleus, what happens is a single proton gets converted to a neutron, and then while conversion, since proton is positively charged, neutron is neutral, so that means this positive charge of proton must be carried away by something. So that carrier of that positive charge is a positron, right? For example, I have a daughter nuclei which is X, mass number is A, and I'll say proton number is Z. Here, one proton will get converted to neutron. So in the daughter nuclei, this is the parent nuclei, this is the daughter nuclei. Since proton is getting converted to neutron, mass number remains the same. But since Z is the number of protons, so one proton is reduced. I'll say Z minus 1. And since it is getting converted to neutron, the positive charge of the proton must be carried away by something. That carrier will be my positron. And also some energy which is being released in this process will be carried away by the neutrinos. Now, what are neutrinos? Will come back later. I'll tell you in detail, but for now, let's say these are carrying away the extra energy. In terms of proton only, if you ask, I'll write a proton is getting converted to neutron and the positive charge carrier is my positron and extra energy is being carried away by the neutrinos, and this is the antiparticle of the electron, and this way we get the positron emissions. Right? So I say positron emission takes place when a proton changes to neutron in an unstable nucleus with lots of protons. This is the equation, and we say that these emissions do not occur naturally. Naturally, we never get positron emissions because it is very difficult. Second, how do we get them is we need to excite the parent nuclei to get converted to neutron. जब हम किसी भी nucleus को excite करेंगे by some sort of energy, either by the photons or the radiation energy or the vibration or the temperature rise करके, so in those cases, protons which will have the sufficient energy for this process will get converted to neutrons and we get the positron emissions. Now, when we are talking about particles and antiparticles, so this is very clear that every particle in this universe has its antiparticle. But who was the first one to talk about these antiparticles? We say that here we are talking about the positron, which is the antiparticle of an electron. But we say that much before positron was detected or discovered, Dirac was the first one who in 1928 talked about the antiparticles. So we say he was the first one to predict the antimatter in 1928, which was before the positron was discovered. Around that time, it was also concluded that, see, we have a particle, we have its mass, but few particles have rest masses also, right? Because when they move with such high velocity, which is comparable to the speed of light. In those cases, we say they do not have motion masses, they just have the rest mass energy. So that rest mass should also be considered or involved or included in the mass conservation laws. The basic conservation laws are conservation of mass, conservation of charge, conservation of momentum, conservation of energy. So in those fundamental conservation laws, we say the rest mass should also be included, right? Then what did Dirac told about the antiparticles? So Dirac, when he talked about the antiparticles or the antimatter, he talked about a few concepts, or you can say a few properties. He said that for every particle there is an antiparticle which will have three characteristics. One is it will annihilate the particle and itself when they meet. We have already seen this, right? And converting their entire mass, because they are vanishing. So the entire mass plus their kinetic energies totally will get converted to the photons, because photons will now carry the energy. Next, they will have the exact same mass as the particle itself, because they have to be equal. Also, if my particle is charged, I'll say the antiparticle has the exact opposite charge as the particle, so that charge is also conserved. Now, Dirac also predicted the reverse process, which is the pair production, because everywhere we are talking about the annihilation process, where the particle colliding with the antiparticle is radiating photons in opposite directions. Why opposite directions? In this cases, because conservation of momentum is also be observed. So we see here they are cancelling out the initial momentum, and here they are carrying away the final momentum, and hence the momentum conservation is also obeyed. Now, the opposite of this is pair production. Pair production, you can also say the best example is the creation of universe. So we say there is a radiation energy in the form of photons, and this energy at some point gets converted to a particle and an antiparticle which just flew up in the opposite direction. This is just a prediction. These are not the exact directions. But we say यहाँ पर भी charge will be conserved, mass will be conserved, momentum will be conserved, and energy will be conserved. All the quantities have to be conserved for every possible process in this universe. So in this case, I'll say there was some radiation energy in terms of photons, and this energy was converted to the rest masses of two particles, which was one was particle and another is antiparticle. You can say the universe and the anti-universe, and this process will be known as the pair production, and Dirac also talked about this process or this possibility. Now, before we move on to the details of these two processes, rest mass energy, we all know it is the, see, it's a famous formula, E is equals to mc square, Einstein ka formula hai, but when I say it's m naught, that means the particle I'm talking about, this energy is only related to its rest mass when it is at rest. So this is my rest mass energy, and in general also when we talk about the energies of the particles and antiparticles, we talk about these energies in terms of MeV and not in joules. Why? Because 1 MeV is around 1.6 into 10 to the power minus 13 joules, or you can say 1 electron volt is basically 1.6 into 10 to the power minus 19 joules. This is the charge of the electron, so it's in joules, and it is the amount of energy transferred when an electron moves through a potential difference of 1 volt. So this will be my basic unit when I'll be talking about the energies of my particles or the antiparticles, and basically when I'm talking about the elementary or the fundamental particles. Clear? So when we draw the diagrams for the annihilation and the pair production, we get to know a few basics again. So what are the basics? I'll see here P means particle, P bar means antiparticle. So I'll say a particle and an antiparticle, they come and they collide and they annihilate themselves, releasing radiation energy in terms of gamma photons, right? So when I'm talking about the particle and the antiparticle, they will have the rest masses. So I'll say particle plus particle give me 2 photons because I need to conserve the momentum also. So I'll need 2 photons. So I'll write gamma plus gamma. Now E naught will be my rest mass energy, and as I said that particles and antiparticles will have the same masses. So they will have the same rest masses. So I'll write E naught plus E naught will give me HF, which is the energy of a photon moving with frequency F, again HF, and I equate, so I get the minimum frequency HF minimum, or the minimum energy that this photon will carry will be equal to the rest mass of the particle, right, which is in general for electron is 0.511 mega electron volt. Now in case of pair production, what will happen? In case of pair production, I am saying there is just one gamma photon which is getting converted to a particle antiparticle pair. So I say gamma is giving me P plus P bar. Now energy of the gamma photon will again be HF minimum, and this will be E naught plus E naught. You cannot break it or divide it, so it will be E naught plus E naught. So in this case, in case of pair production, the minimum amount of energy carried by the photon needs to be 2 times the rest mass. बेसिकली यहाँ पे 2 फोटोन बने थे, यहाँ पे 1 फोटोन है, तो दिस 1 photon is equivalent to 2 photons, so basically the double, and again the rest mass for electron will remain the same, which is 0.511 mega electron volt. Now see, now we know that whenever elementary particles are interacting, pair production is happening or annihilation process is taking place. So basically there are interactions which are occurring between the particles and the antiparticles. Now these interactions can be between particle-particle, antiparticle-antiparticle, or between the particles and the antiparticles of another pairs. But we say ki how does these interactions take place? Now let's take a common example. We know that Newton's laws were, first was ki if you do not interfere or you do not apply an external force, the body will retain its inertia. That is, if it is at rest, it will remain at rest, and if it is moving, then it will keep moving. Then the second law was that if external force is not applied, then the momentum of the body remains conserved. F was equals to dp by dt and it was 0. So I said momentum is conserved. The momentum conservation law came out from that. But now I say कि whenever I'm saying that some force is being applied or is acting on some particles, so we say that force is impacting that particle by transferring some amount of momentum, right? Momentum is mass into velocity. So I say when I push a wall or when I push a car, so the force which I am applying is carried away by the momentum, which in turn is obtained by the object. So in the same case, the third law said that every action has an equal and opposite reaction. So a force which is the action force, I am denoting it by a vector sign, and it is equal and opposite and is the reaction force. So in this case also the momentum is the force carrier, I'll say. So I say that similarly during the particle interactions, ab dekho, when I'm talking about normal interactions or the macroscopic interactions, in those cases my momentum is carrying away my force. But in case of particle interactions, there must be something which will carry away the force. Like if I'm talking about the electromagnetic interactions, then the electromagnetic force which is being exchanged between the particles will be carried away by something. That something will be my virtual photon. And this was predicted or it was told by the scientist named Richard Feynman. He said that whenever elementary particles will interact, they will have electromagnetic forces acting on each other, and this force will be carried away by a virtual photon. Now, why are we calling a virtual photon? We know there is a photon which is the I can say quanta of light, and it is moving with the speed of light. It has zero rest mass. But why am I adding the word virtual? Is because when these interactions are taking place, the quantities are so small that I cannot detect these photons directly or without interfering, right? If suppose I am observing or detecting these photons, that means I have to you can say collect them, or I need to absorb them on some photographic film or something, and this absorption or this interference may change the course of the interactions. So we say that we cannot detect them directly or indirectly, so we have named them the virtual photons. So that is a theory, and these photons, these virtual photons, are also represented by waves. The gamma photon is anyway represented by a wave, but here we say that the virtual photon will be represented by a wave, and this wave वाली diagram जो भी हमारी interaction की बनेगी will be known as by Feynman diagram. Like here I have few particles, every p represents some particle or the same particle, it doesn't matter, but when they are colliding or when they are interacting, the intermediate transfer of this electromagnetic force is done by this virtual photon, which is represented by a wave, and this whole diagram will be known as the Feynman diagram. So I'll say this is the Feynman diagram, I'll say this is the Feynman diagram, I say this is the Feynman diagram. Clear? Then now let's take some analogy, which is a good analogy. I'll say कि I'm standing here and I'm wearing these ice skates, and I'm standing over the ice only, where there is I can say ideally or practically zero friction. I have a very heavy ball and I have the similar person standing in front of me, and I just pass the ball. So according to Newton's third law, when I am applying the force of action in this direction, I will experience a force of reaction in this direction, right? Similarly, the person, I will move back, but when I am passing this ball will carry my momentum in this direction and will transfer to the person standing in front of me. So basically when I'm passing the ball, due to reaction, I will move this side, and since this ball is carrying the momentum, this person will move away. So this you can say are the like charges. They will repel each other, and the momentum carrier here is a ball. Next is, I can say, opposite charges. So here I am the same person standing in ice, but this time I have a boomerang and I just throw it in the opposite direction. So as the boomerang moves, it will move back and it will come from this side to the person standing in front of me, and as a result of my reaction I will move backwards, and this person carrying this momentum transferred by this boomerang will also move towards me, and we attract each other. So in this case also, the momentum carrier will be my boomerang. Similarly, we say that in case of the elementary particles, this exchange of momentum is carried away by the virtual photon. So we say that this virtual photon here is the hero or the Salman Bhai of all the interactions or the elementary particles interaction. Right? So these were my particle interactions, virtual photons, annihilation, particle antiparticle, and yes, the hero of the particle interactions. I hope this is very clear to you. If not, do leave me in your comment section what are your doubts and which topics you want me to repeat, and till we bring the further topics, stay connected, stay tuned. Thank you so much, and don't forget to like, share, subscribe to my channel, which is Teacher Cool. Thank you.